Okay, so if you remember back, I forget how long ago it was, but we talked about the queue, which stored elements in a FIFO type way. Can anybody tell me what FIFO stands for? First in, first out. Okay. Which means first come, first serve, no cuts. The element that's added to the queue the element that is added to the queue temporally first will be the first one that is removed when you call the methods on queue and dequeue. I believe it was. So on queue, add something to the end of a queue. Dequeue removes it from the front. That is how you add and remove elements. Today, we're going to be talking about the queue's brother or friend or twin, whatever you want to call it. Stack, these two are often talked about together because contrary to the queue, the stack is a LIFO data structure. Does anybody want to take a guess as to what LIFO stands for? What? Last in, first out. Oh, I don't know why I added the dashes. So, in contrary to the queue, when you add elements to a stack, you add it in what's known as the top. And then when you remove them, you also remove elements at the top. You can think of it like a stack of books. If you have a bunch of books that you want to read, if you want to get to, say, the book that is third or second from the bottom, you first must remove the book that is on the top and remove the book that is on top of that. You can't simply, you could grab the book in the middle, but it would completely destroy things. So we're not going to do that. Or a stack of stones, or a stack of pancakes, anything you want to think about. There's lots of stacks in the world. Pick one as a proxy for the stack. Putting elements onto the stack, you add them, push, and then removing is a method called pop. Way more fun than on-queue and queue. So you push elements onto the stack, you pop them off of them. You might be thinking that's kind of weird. Why would you have a data structure where the only way that you can add elements is through one specific location, and it's the top of the stack? But stacks are actually very useful. The most common example that I like to give is a web page. So if you go to a web page and then you click the back arrow or the forwards arrow on your computer, that is a stack. It memorizes all the websites that you've been to. Let's say you go to Carmen, and then you go to YouTube, and then you go to TikTok in the browser for some reason, and then you go back to Carmen. If you hit the back arrow, what it's doing is it's just taking the current or taking the most previous website that you went to off the top of the stack, and it's doing that over and over again. So that's one way that a stack could be implemented. Undo and redo in Google Docs, also a thing, could be implemented in the backend as a stack. So there are some benefits to keeping the temporal time of when you did something or the last thing that happened, and a stack is how you do that. But other than that, stacks are pretty similar to queues, as you will see, and so pretty similar to all of the other data structures that we talked about. So the stack component allows you to manipulate strings of entities, arbitrary type in LIFO or last in, first out methodology. It's kind of a dual or a little brother or a big brother to the queue. And then first and last refer to the temporal order in which entries are added, not in terms of the string of entries. So like we talked about previously, when you're talking, stacks are modeled by a string of something, in this case, the generic type T. If I give you a mathematical string of 4, 5, 6, and 7, you really should not be able to tell whether this is a queue, whether it is a stack, whether it is a sequence. You might be able to tell if it's a set. It has, say, this was 6 instead, because sets cannot contain duplicates. But the main takeaway is that all of these are modeled based off strings of entries. It's just how you reason about adding to, removing from, and dealing with the elements within them that separates the queue, the stack, the sequence. So keep that in mind. They're all just modeled by a string of T. So here's that image again, once again. Standard has contracts for 3 methods. Oh, I was going to ask you what they were, but they are clear, new instance, and transfer from. Again, all of the OSU CSE components implement from standard. It is the grandfather of all OSU CSE components because everything needs clear nuisance transfer. Stack kernel is only going to have 3 contracts for kernel methods, which are push and pop, the one that I talked about over there, as well as a length variable, which you can probably guess what it does. And then it only has 3 additional methods, which are top, replace top, and flip. And you could probably use context clues to see what those do. But we're going to go through examples of them because aliasing, as always, is evil. Here's that mathematical model again. Type stack is modeled by string of T, same as type Q, same as type sequence. Same as type set, although set can be duplicates. Only has 1 constructor, which creates an empty stack. Here's an example of that. We invoke it the same way that we would a queue, or a sequence, or a set, where we include the name of the interface inside of the chart that we're trying to define. In this case, we're saying, hey, give me a type stack. I want it to hold integers. So we're using the big integer as opposed to the little int. Java will do something called auto boxing, which allows you to store integers like big integers, which makes them reference types. Saying call it SI and something. And then we're saying it should be of type new stack 1L. Where stack 1L is an implementation of the stack interface. Remember, we have this separation. We haven't talked about it in a while, so I'm going to remind you. We have this separation of concerns where interfaces only describe what that class ought to be able to do. So a standard describes what should a standard thing be able to do. Well, it ought to be able to clear itself. It ought to be able to transfer itself to another type. And it ought to be able to make a new instance based on the dynamic type. It says, I don't care how you do it, but that's what it should be able to do. It's like a boss or a manager that only wants to give you instructions, or the ideas guy of a startup. Same with stack kernel. Stack kernel says it should be able to push, it should be able to pop, it should be able to give me its length. How you do it, I don't care. Just make it do it. Same with stack. Stack 1L and stack 2 are the, I guess, the interns of the company who do the actual work. They say, okay, well, my boss says that I should be able to push, I should be able to pop, I should be able to get the length. And then I should be able to do all of the other 6 methods that I'm inheriting from because of object-oriented programming principles. Here's how I'm actually going to do that. And that's where the Java code comes in. So keep that in mind. Remember that. Important things. And after this is done, what we have is we have an empty mathematical string because stack is modeled by a mathematical string. And so there's your stack called SI. Okay, now we're going to get into the methods. So I'm going to erase this so that we have space to draw our stack. More pictures today. So get excited for that. All right, so the first method that we're going to be talking about is push, how you add elements onto the top of the stack. I'll go through the method first. Pushes X to the top or the left end of this, creates an alias to X, updates this, ensures that this is equal to a mathematical string containing only the element that you want to push on top of the stack, concatenated with the old value of this, which was the stack before you called the push method. For visual purposes, I'm going to draw the stack like this, as opposed to the normal way, just so that you can see the vertical structure of the stack, where 70 is actually on the bottom of the stack, and 3 is on the top of the stack. Typically, when we use tracing tables, the left end of the mathematical string corresponds to the top of the stack. So if you take your mathematical string, 3 and 70, what that actually looks like is 3 and 70. I don't know how to do, I guess like that. It's like a Christmas tree or like an elevator thing. Okay, so keep that in mind. Picture-wise, I'm going to draw it like that because it's easier to understand what the stack is doing if you draw it like a stack. It's a stack of references in this case. So we also have K, which points to, let's call that up. And then we have K, which points to an object value of 49. Now, when we call push, we are adding a reference location onto the top. We're saying pointed towards the object location pointed to K. And afterwards, we have a stack of 3 values now, where 49 is, again, the leftmost value in the mathematical string, and then it's 3, and then it's 70. Notice the alias here that has been created. Very bad if you have mutable reference types, such as integer natural number. Not so big of a deal if you're storing a stack of like XML trees or simple writers. Yeah. Questions on push? Awesome. Alias here. You should be able to draw the appropriate diagram showing it. So you should be able to do that, what we just did. Make sure you can draw pictures. Pop removes and returns the entry at the top or the left end of this. Updates this requires that this is not an empty stack. You can't pop something off of an empty stack. And ensures in contract language that the old value of this is equal to the mathematical string containing just the element that you popped off, concatenated with this. So here's our example. Is it the same one? It is. Perfect. So I'm going to redraw it though, so we can see what the actual stack looks like. We now have a stack of 3 elements where, again, the leftmost value of the mathematical string is the one that's on the top. Z is just a random reference value pointing towards -584. And we're saying that Z should be reset to the reference value or the object value of whatever is on the top of the stack, which in this case is 49. So you remove the top reference location and say, hey, take that object value, whatever it is, and point Z towards it. And so now afterwards, we have 2 elements of the stack. You'll see that 3 is going to be on the leftmost end because it's the top of the stack, and Z is going to be equal to 49. Voila. Questions on push and pop? It's kind of the same as on QDQ. Make sure you're comfortable drawing pictures of this, though, because it will help a lot, especially if you get asked a question about drawing, which you might. Who knows? I don't make the final. All right, this is the difficult one. Length reports the length of this, so I'm going to ask it again. Oh, it doesn't even have an example. All right. If I have a stack of 2 elements and I call si.length, what will it return? 2, thank you. If I have a stack of 3 elements, what will it return? Perfect. That one's a toughie. Okay. Top returns an alias to the entry at the top or the left end of this. Say alias reference returned by top. Requires that there's an actual element in the stack and ensures that top is the prefix. If you remember back to our mathematical string, actually the prefix is the first element of the mathematical string. So if we have, in this case, the mathematical string is 3 and 70, we're saying that it's meant to ensure that the alias is pointing towards the 3. Okay, more pictures. Looks like we have the same stack, 49, 3, 70. And we have A, which is pointing towards some random value, -58. Here we're saying, hey, I would like to see what the top value of the stack is. Maybe because you don't want to pop it off before you know what it is. Maybe just because you're curious. But what this does is it resets the reference of K to 49. Notice the aliasing there, very dangerous. So afterwards, K will be equal to 49. These 2 49s, again, the same thing because they are referenced or aliased. And then there's our little warning for aliasing. Okay, replace top replaces the top of this with X and returns the old top. It's kind of like replace front in Q. Aliases, the reference to X, updates this, requires that this is not an empty stack, and then ensures mathematical location that the element at the top, replace top, is a prefix of the old value of this, and this is equal to the concatenation of whatever you're replacing with every element that's after the old value of this. Essentially, replacing the top. Okay. Now we have. They switched up the structure. Now we have a stack, K's two elements, 49 and 70. We have K, which is pointing towards an element of -58. And then we have J, a value of 16. So we're saying K should be equal to the value of SI dot replace top, where the value which we're replacing at the top is J. So first, K should be equal to the old value of the top based on our contract. So K should be equal to 49. And then J should equal the old value of the top. J should be, no, I did this wrong. Ah, geez. Okay, this is why I try to picture yourself. K points towards -58. Wait, did I do it wrong? No, I didn't. I did it. J is equal to 16. K should be equal to the old value of the top, and then the old value of the top should be now, instead of pointing towards 49, to 16. This is why I draw and picture yourselves. So the value of the stack should be that 16 and 70. 16, 70. K is equal to 49, which was the old value of the top, and J is still alias to 16. Next is probably going to be a simplified version where you just swap them. Yep. So if you just want to swap values, you can make things a little bit simpler on yourself. Back to the old picture where 49, J is 16. K, you're no longer needed. Goodbye. Here we're saying J should be equal to SI dot replace top. So this swaps the values of J and the top of the stack. So now the top of the stack is 16. J is alias 249. And we don't have to worry about any dangerous aliasing because there's no two reference values that point to the same object value, which is nice. Swaps J with the entry previously at the top. Okay, that's replace top and top. Any questions on that before we move on? Okay. Flip. Reverses or flips this, takes the stack, flips it on its head, updates this, ensures that this is equal to reverse again from string notation of this, the old value of this. So if we have a stack which is 18, 6, and 74, and then we call dot flip, what will be the value of the mathematical string of the stack afterwards? Yes, exactly. Just the reverse of the reverse of the stack. Okay, that is the stack. It's hopefully not too bad. Any questions on that? Just another typical CSV component. This part of the class, you kind of just do this a bunch of times. And then it's really the last topic we cover. And then we spent 2 weeks talking about Java graphics for some reason. And trust me, this is way more fun than the graphics. So. Now that we know how the stack works, we are going to peel back the final layer of ignorance about recursion, and we're going to tell you how recursion actually works in Java's memory. Remember, we talked about what recursion was, how you should think about it, and how you should reason about it. Now we're going to talk about why recursion works. So how should you think about recursion? You should pretend that there is a free lunch class with the same method and the same contract that only works for smaller problems, and then suddenly realize that the ground truth of it all is that there is no free lunch. Then we talked about why do recursive methods work, or how to reason about testing to make sure that your recursive methods do work. And the strategy that we talked about for that was to start with the smallest possible case, prove that if it works for that, and then it works for the next smallest case, and then it works for the next smallest case, then you're probably good. So does it work on all the smallest cases? Does it work on the next smallest cases based on the fact that it works on the smallest case? Does it work on the next smallest case based on the fact that it worked on the previous smallest case, which is based on the fact that it worked on the smallest case, and so on and so forth. You can probably prove that your recursive method is good enough for government work. Now we are finally going to talk about the third part of it, which is how recursive methods work. I promised you guys that we would come back to this, but we continue to advise that if you insist on thinking about recursion this way, rather than simply sating your curiosity about how it works, interesting word, you may never be fully capable of developing elegant recursive solutions to problems. Essentially what they're saying is that this is a complicated way to think about recursion. So if you're writing a recursive method, you should not be trying to think about how it works in the back end, how Java thinks about recursion, because if you do, you will confuse yourself. And that I actually do subscribe to, because as you'll see, it gets a little bit hairy. Here's the example that we've used so oft before, which is of a reverse string. If the length is s, or if the length is 0, we just return. So that's the empty string. Else, we chop off the right half, we reverse it, and then we add the character back onto the end. That's the base recursive example that we've been using. So in your tracing tables, here's what we've been advising you to do, which is just when you get to the recursive call, pretend that the method contract works. So pretend that reverse string, what it says it does is that it reverses the string. You can just pretend that if you pass in sub to it, it reverses the string correctly. But how does this actually happen? This is a recursive call, so how does it work? How does Java treat the recursive call? And that begs the question of how does it treat any call that is not just simply Java code that can be executed? When you call the length method, you know that it returns the length of a string, but how does it actually go about doing that? When you call the xml.numberofchildren method, how does it go about calculating the number of children? As the client, you've been looking at the contracts for these methods throughout the entirety of the class. And because you're the client, you don't have to worry about how they work, either conceptually, how it counts the number of children, or in Java. You kind of just call the method and the answer is served up to you on a silver platter, which is the goal of design by contract and splitting things into client versus implementer view, is that you don't have to worry about how number of children works or how it is working in the back end. You can simply just call the method and somebody else has done the work for you. That's the beauty of client implementer programming. But we're going to talk about how it works anyways, because it's important to know. Okay, so anytime that you have a method in Java that gets called, the tracing table for the code, or what's known as the stack trace, is suspended, and that tracing table, or the stack trace, is pushed onto the runtime stack. So Java has in its backend memory this, what's known as just the runtime stack. Which, when you start a program, pushes the main, or it's empty at the beginning. And your main may have some variables, you may define some variables, but as soon as you call a method that is not within the main stack, what happens is it suspends the main thread, or the main stack trace, pushes it onto the runtime stack, and then goes into that separate method where you can define other new variables, you can call other methods, and so on and so forth. When that method returns, either with a value because it's a integer method or a double method or a Boolean method, or doesn't return anything because it's a void method, this main thread is popped back off the stack. It says, hey, remember me, you still have work to do. Maybe you've computed some value that is now useful to you in main, but that runtime stack gives you back the context of what you were working on when you pushed it onto the stack. And we're going to talk about how this works through the context of a tracing table. Essentially just a stack of tracing tables, each partially filled in with results of the code in that tracing table as executed thus far. So every time you call a method, .length, .number of children, et cetera, a new tracing table is created containing the code for the method body being called. The argument values are copied from the suspended tracing table into the formal parameters, either copy by value or copy by reference. And then execution in the new tracing table continues until either it calls a method or it returns something else. So if we have just regular code, let's say that this is the main method. We've defined a string, so this is contained within the stack. We define a string OSU, and then we call if s.length equals 0. What happens as soon as the tracing table, or if you're in Java, the execution thread gets to this point is it says, hey, stop here. We have to call another method. This method happens to be an instance method called length, which is being called on the string s. There's some value for which we need to calculate because we're calling this method. So the call suspends the current tracing table or the current thread of execution, and the suspended tracing table is pushed on top of the runtime stack. So this runtime stack contains a bunch of information. Most notably, it just contains like the method that we're running. In this case, it's main, and any information about variables that we might have defined. So it keeps track of the fact that we have a string called OSU that is defined. So we've pushed that onto the runtime stack. We are going to save it for later because we currently can't finish the execution of this code without knowing what the length variable of s is. There's a piece of information that we must get from the length code first. And so now we have a tracing table for length, where this, which is the distinguished formal parameter, is equal to OSU, and there's some method body for the instance method length. So the tracing table, or the thread of execution for the length method, begins. Here's the contract for that if you've never read it. Body for the length method. Oh, wait, never mind. It's not the contract. It's just saying to look at the contract. But the contract says that it returns the length of this. So this is the current thread of execution. We have this is equal to OSU. Some code is going to run which counts the number of characters or returns the length back to you. So now we have that length is equal to 3. And we hit this, or we will hit a return at some point. When the currently executing tracing table, so in this case, the one for the length method, reaches a return statement, or for a void method, falls off the end of the body, the results of the call are reflected in the tracing table on the top of the stack. So this right here has a bunch of results, has a bunch of variables. What we care about is either nothing, if it's a void method, because it's not returning anything to us, or we might care about what the return value is going to be. In this case, the return value is going to be an integer, the length of 3. That tracing table is popped off the stack, and it becomes the currently executing tracing table, resuming execution from the point where it was suspended. So when we calculate after we calculate the length of the string, the results are reflected in the calling table. This stack, which we pushed off for later, if you remember, says, all right, it's your time again. Get back up here. It's time to continue. And it is popped to resume execution. So this comes back up. We say, well, remember all that stuff we had? We had a string called OSU. And then we stopped you because we needed the value of the length. Well, now we have the length. The length is 3. And then execution can continue to the next call. So what happens here is now we have no new variables because all we were using is the return value of s.length to check if those equal to 0, which it's not, 3 is not equal to 0. And so what happens now is we say, okay, well now we need a string sub, which should be equal to s.substring. Well, substring is a method. So what happens, we push the main method back on the stack because now we must call the substring method. It's important to note that let's say you get into the substring method and it calls another method. Let's say it calls the length method, then the substring method would get pushed on top of the stack with any variables that it might have, and then it might go into the length method. And then when the length method is done, it pops the substring method first off the stack, and then the main one back off the stack. So it's a way to keep track of how deep through the rabbit hole you are going in terms of methods calling methods calling methods. And methods calling methods calling methods might sound like something. Recursion, so we'll get into how that happens. How are we feeling about this so far? Okay, I see a thumbs up, so I'm going to keep going. Okay, so we're going to pretend that that works because we can pretend it works because client implementer contract. And now we get to the next call, which is a recursive call. But there's nothing special about a recursive call. it works exactly the same as any other call. So the main thread of execution here that we have is that S is equal to OSU. We have something called sub, which is equal to just the string SU. And what happens here is we push this back onto the stack, and then we start another recursive call, which has the same exact code. So the current tracing table is suspended and pushed onto here, and a new table for the body of the method is called. Where the only difference now is that S in this case is equal to SU as opposed to it equaling OSU in the beginning. Begins it with its own variables and values. Soon, this reaches a recursive call. In which case, this execution, which I'll just call reverse sub 1, gets pushed onto the stack with all of its variables, where S is equal to just the character S, now it's SU, and sub is equal to just the character U. And what we do is we push this execution onto the trace or onto the stack of tracing tables, and we start another tracing table or another thread of execution. For this time, S is equal to U. And you could probably guess what's going to happen now. We are going to reach the recursive call, and we're going to add this stack trace onto the stack. We're going to add this tracing table or this thread of execution onto the stack. So we have reverse sub 2, which has its own variables, where S is just equal to U, and sub is the blank string. Like that. So finally, we start a new call where the body of the method is just this, because we have hit what's known as the base case. And then that tracing table returns. So it just returns the empty string. What happens now is that the results are reflected in the calling location. As you can see, based on the runtime stack, we have 3 different calls to reverse sub, because that main method is just a call to reverse sub. That we now can populate with results from the recursive calls. So that first one is popped off the thread of execution, with the result being just what was returned from the most recent call to the recursive method. And then that tracing table returns. The next stack is popped off the stack, or the next stack traces were popped off the stack, or tracing table is popped off the stack with the results from the previous one, and so on and so forth, until finally you just have your original or final string USO. This is why you have to have a base case, and you have to make the problem smaller, because otherwise what happens is you have your runtime stack and you just keep adding things on top of it. And eventually Java runs out of memory and overflows. So you have your stack and it falls over. And if you've ever been to Stack Overflow, probably not, because everybody just uses ChatGPT now. But Stack Overflow is like a forum where people ask questions about code. That is where it gets its name from, is what happens if you don't have a base case, or if you don't make the problem smaller. You will just build up stack traces, thousands, millions of stack traces, and then eventually Java will say, hey, I think there's an issue, and crash out on you. But yeah, that's pretty much it. Each call to a method, whether recursive or not, effectively results in the creation of a new tracing table. Each tracing table has its own variables, its own formal parameters, its own local variables, each method as well. And you just push them on top of the stack, calculate the new values, and then eventually, when the thread of execution reaches its end, where you reach your base case, you slowly but surely pop all of the stack traces off of the stack in order to complete the method. And that's how it works. If you really think you can reason about recursive code by mentally executing this kind of series of events to check your thinking, then you're deluding yourself. I think for small cases, it's valid to, I even did this in some examples, to separate the stack traces up into different calls. So S is equal to OSU, and sub is equal to like SU, and then pass the values in there. I think that can be a totally valid way to think about recursive methods, but let's say you're calling a reverse string on like a 20 character long string. It is not practical to trace through all 20 recursive subcalls and keep track of all the variables because you will get confused. It's just too many recursive calls. But for small examples, for testing out small examples of recursive methods that you may write, I think it is a valid way to do it. Just don't get too carried away. If you don't believe this, try mentally executing this way for code that makes multiple recursive calls from each tracing table. Again, small examples, I think it can work. When you're debugging, you can actually trace through the stack trace. So you can click on each subsequent stack trace and see what the variables look like. Pretty useful if your recursive methods are not working practically, but people are packing up. So I think they see the 50 at the top of the screen and they think it's done. I still have you contractually for 15 minutes, but are there any questions about stacks or recursion or anything? Yeah.
If we are drawing a stack for like the test, is it fine if we draw it vertically like you did, or should we draw it like the other?
You can draw it vertically. I'd actually prefer it because it'd be easier to look at. It's like a stack.
Okay.
Yeah. This doesn't change things about tracing tables for recursion. If you have a recursive tracing table, you should still just pretend that the method works like you did on the last midterm. You should not trace into multiple tracing tables and draw multiple tracing tables. That is not how we do that in this class. That's how it works behind the scenes, but for abstraction purposes, we just pretend that the recursive method works because it does, usually. Okay, other questions? Okay, gift of time. You guys can get out of here 15 minutes early. Enjoy the day. Put that back.